Hello, this is Patrick Hugh, attending from Perth in Western Australia. It's my pleasure today to talk about using watershed graphs for faster path planning in binary occupancy grids. The research arose from work on trajectory planning for a quadcopter drone. Here's the problem. We have A* searching for a grid path from the source in the top left quadrant to the goal at the bottom right corner. Under the Euclidean heuristic, A* explores towards the goal and gets trapped in the dead end. It then has to laboriously backtrack out of the dead end, fighting against the heuristic all the way. All of this backtracking takes time. The underlying issue is that our path planner, A*, is only looking at the local terrain. From where it is now, where can and should it step next? Instead, we want the planner to consider the terrain's global topology, to steer towards choke points that must be traversed or away from dead ends. The idea has received quite a lot of attention, especially by researchers in AI for games. When I was reviewing that research, some of the work reminded me of the watershed transform from digital image processing. I decided to see what would happen if I applied it. The result is the watershed graph. In this talk, we'll see how to construct the watershed graph, how it can be applied to help path planning, and how much it helps. There are 9 steps to construct a watershed graph, as written out here. We will work through each step. Step 1. We restrict attention to a single connected component of accessible cells, generally the largest one in the terrain. That's because if the source and goal are in different connected components, then we know that there is no path between them. Step 2. There's really only one big idea in this work, and this step is it. Take the terrain. Calculate the distance transform of the accessible cells, that is, the Euclidean distance from each accessible cell to its nearest blocked cell. Obtain the complement of the distances. We get a height map where the blocked cells are the high plateaus, and as the distance increases from the blocked cells, the height map descends to its deepest points. Now apply Meyer's 1994 watershed transform. We get basins, shown here in different shades of grey, separated by ridges in blue. The insight is that ridges can form at choke points in the terrain. So now we can cue our path planner. If it's in the same basin as the goal, then head to the goal. Otherwise, it should leave that basin via one of the ridges. That's the big idea. Apply a watershed transform to the complement of the distance transform so that the ridges are indicators to choke points. And what we're going to do with this idea is equally simple. First, we're going to put pairs of nodes across each ridge, connected by a line segment. We will call these transits. And second, we connect the nodes that are in the same basin. What we get is a graph, the watershed graph, that captures information about the global topology that we can use to speed up path planning. So let's see how the transits are obtained, steps 3 and 4. We look at the basins that touch a ridge. They are shown here in different colors. The transit minimizes the round-trip distance between the basins when going via the centroid of the cells that touch the ridge. That is, from one color to the other when going via the centroid of all the colored cells. This construction builds transits that are weighted towards the middle of the ridge. It also handles atypical cases such as this one on the right, where we have multiple overlapping ridges. That takes us up to step 4. The remaining steps are to build the graph. The core idea here is that if nodes are in the same basin, then they should be adjacent in the watershed graph. The little thing we have to handle first is the cells in the ridges, because they do not belong to a unique ridge. So let's fix that issue by doing a flood fill. Step 5. This creates a segmentation of the accessible cells. Every accessible cell belongs to a unique segment. Now we can set up our watershed graph. We initialize the graph as being the transits. That's step 6. Step 7 is to add the goal. Step 8 is to put edges between nodes in the same segment. And then step 9 is to run Dijkstra's algorithm to calculate a distance via the watershed graph from the goal to each node in the graph. That's it. To recap, the big idea is to apply a watershed transform to the complement of the distance transform so that the ridges are indicators to choke points. Then there is a bit of detailed work to put transits across the ridges and grow the graph, but that's it. Steps 1 through 6 are performed whenever the terrain map changes. Steps 7 through 9 are then performed whenever the goal changes. The output is the watershed graph, a distance to the goal from each node, and a segmentation of the accessible cells. We now use the model to cue pathfinding. There are 3 applications of the watershed graph that I could think of or that I could see in the literature: set a heuristic, set subgoals, or block out cells. The watershed graph heuristic is distance via the watershed graph. For subgoals, we use the nodes from the shortest path through the watershed graph. And cell blocking gets the segments that are traversed by the subgoal path and then sets all other cells to being inaccessible. Here's what it looks like. The path on the left was planned using the Euclidean heuristic. The paths on the right used the watershed graph. As the watershed graph cues the planner, fewer locations have to be explored, so there can be a net saving in runtime. But it's possible that the resulting paths are longer. I tested each application using 3 path planners: A* for grid paths, Lazy Theta Star, and Phi Star. The tests were run on the Moving AI Benchmarks 2018 version, covering game and street maps, maze maps, room maps, and random maps. The hypothesis was that the watershed graph would yield a net reduction in runtime, though possibly with an inflation in path length. The baseline for comparison was path planning under the Euclidean heuristic. The first question of interest: is the investment in the watershed graph actually ever recouped? So this chart shows the break-even path length, the path length in the benchmark set when there is a net reduction in runtime. Earlier break-even is better. Under all 3 applications of the watershed graph and across all 3 of the path planners, break-even occurred on game, street, and room maps. The path length was on the order of 50 to 150 cells, noting that the maps were 512 by 512 cells. Break-even was not achieved on maze maps when corridors were thin, nor on random maps when the fractions of blocked cells were low. The second question of interest: how much speedup is possible? This chart shows the largest speedup factors that were observed. Larger speedup is better. Factors on the order of 5 to 15 times were observed in favourable cases, namely SC1 game maps and the street and room maps. An unanticipated behaviour was that the speedup factor could decrease as path length increased. The likely cause is that very long paths achieve their length by traversing large portions of the map. So path planning ends up exploring the entire map anyway. The third question of interest: what is the impact on path length? This chart shows the largest path length inflation that was observed. Smaller inflation is better. Across all three of the path planners, setting sub-goals caused the greatest inflation, on the order of 20%. The heuristics suffered the next largest inflation, on the order of 5%. Cell blocking suffered no inflation except in rare cases. Path length inflation was especially acute on maze maps and increased with corridor width. This is likely due to the transit's locations being weighted towards the centroid of ridges, pulling them away from the blocked cells. For in the shortest path, changes in direction are tight around corners. Overall, I concluded that the watershed graph can speed up path planning if the terrain contains rooms and choke points, and the paths being obtained are long but do not fill the map. Hence, watershed graphs could be helpful in interior, underground, or urban terrain, but would be less helpful in forests. For practical purposes, the payoff may not be in the absolute reduction in runtime, but in adopting calculations that could be pushed off to GPUs. Likewise, we've seen a connection in theory between path planning and digital image processing that invites further investigation.